Hi, this is Jeff Heaton. Welcome to Applications of Deep Neural Networks with Washington University. You know what? Maybe we humans are overrated. After all, AlphaZero was able to master chess in hours without even the benefit of human knowledge. We try to do natural language processing, and we use all these fancy add-ins like NLTK and Spacey and other things. Maybe we should just let the neural networks try to learn English from scratch, or other languages as well. This is called end-to-end neural networks. For the latest on my AI course and projects, click subscribe and the bell next to it to be notified of every new video. Continuing onward, we're going to look at another type of... Welcome to Applications of Deep Learning with Washington University, and see how we can teach a neural network to learn to read. So these are the two papers that I am pulling this from, based on, and then I'm also using the code from the Keras examples, where the creator of Keras implemented end-to-end neural networks as an example of Keras. This will probably eventually be built into a Keras layer specific type so that you can use this directly, but for now, you see some of the plumbing used to actually implement this network type. And there's also an online JavaScript demo that you can use to play with this if you would like to as well. We are going to go ahead and actually create a end-to-end neural network here and make use of it. So these are just some necessary imports and utility functions that were created in the Keras example. I made some changes to these to make it work a little bit better and eliminate some of the warnings that Python was generating because it was generated possibly on an older version of Keras. I also added a Q&A part at the end. The original code, it trained the network and it gave you the accuracy, but it didn't give you any way to use it. So I created that part at the end. Let's go ahead and run this. It tells you it's using TensorFlow as the back end, and then we see that it is still running. It takes it a little while to load that in, but while it's doing that, let me show you some of the parts that we're doing here. This is the tokenize function. It uses a regular expression to split apart the words of a sentence. So this would turn something like Bob dropped the apple, period, where is the apple, question mark. So this is very much in the tasks form, but this gives you an array of words rather than just one big sentence. So this is called tokenization. It tokenizes the sentence and breaks it apart for you. This parses the stories. So this takes stories that are in Babby task format and breaks them into the three parts. So you will get, and it's sort of separated by tab delineation. I won't take you through all of the steps of this, but basically what it is doing is taking the three parts. The parts are, you'll have a story where it'll say, John walked to the bathroom, Mary went to the bedroom. That's essentially the first part of it, the first of three. The second part is then the question, where is John? Or some other thing. And then the third is the answer. The answer to this type of neural network is always a single word. So you are asking it questions about the story, and you then give it a question about it, and it gives you a word back. The important thing to realize about the training of the neural network is the weights in the training of the neural network are learning to read, not learning the specific sentences. Because after the neural network is trained, you'll give it new sentences, and it should be able to answer questions about them. Because the training data has all sorts of instances of Mary's in the bathroom, Mary's in the bedroom, all different locations. Those are specific to that particular training example. It's not the locations that it's trying to learn. It's trying to learn how to read new stories and be able to answer about them. And then this function here that we call will get the stories by calling the other functions that we just had, the parse stories, and it returns the stories in a vector format that can be passed to the neural network. We finally vectorize the stories. I will show what this specifically looks like, but essentially what it's doing is it's taking all of the sentences, the stories, figuring out how many unique words there are, and then vectorizing them and changing them into pure numeric form where each word has a numeric index that it gets replaced by. And we'll see how that works in just a little bit. This block of code here basically downloads the data. So we're getting the data from AWS and downloading it to this GZ file. Then we extract out the parts that we want. We're doing the 10K challenge. This is a smaller data set, but still fairly big. That keeps us able to run it on our computers. I should point out, too, the computer that I normally run these examples from, we're using a AWS instance like I discussed before. I basically hit my website. You won't be able to use that URL because it's my AWS instance and it costs me money, not a lot. But I normally use a 8 gigabyte instance. To do this class session, since there's considerably more, I actually use a 16 gigabyte. If I was using the bigger data set forms of these, I would need a much more RAM. This might work on a computer with 8 GB. Okay, so we run this. I am going to go ahead and run this portion since I've ran the previous portion. It is extracting the stories for the challenge, and it gets them. Now, I had already run this, so it had already downloaded them. If you were running this for the first time, it will probably have to download those. Let me run this just so you can see what the data actually looks like. So here's a story. Mary moved to the bathroom. John went to the hallway. Question, where is Mary? Answer is bathroom. Here's another story, and these can be multiple sentences. Mary moved to the bathroom. John went to the hallway. Daniel went back to the hallway. Sandra moved to the garden. Where is Daniel? So it needs to read these and find the last location that he said that he moved to. And they describe it different ways. Went back to, moved to, went to. So it really does need to learn to read this. These are just training examples. I need to emphasize again, the neural network is not remembering that Mary is in the bathroom. That's just unique to this particular sentence. And there's a whole bunch of these. There's like 10,000 of these that it trains over. And the answer is always a single word. So it learns to read a sentence like this. And we'll see that in the end, we can make up our own ad hoc story for it. It will read it and then it will answer something about it. But we'll see that it has some very important limitations. So first, we need to build the vocabulary. And this is a very important limitation of this program. We will run that, and let me show you what that looks like. It builds the vocabulary very quickly. What it did is it went over all 10,000 of these training stories and the 1,000 test stories. So we're going to train it on these, and we're going to test it on these. And we're going to see how well it can learn to read. It pulls out some very important maximums here that are going to be implied or imposed on the trained neural network. We have 22 unique words. That's going to be the vocabulary. So if you look over all of those sentences and you count up Mary, move, to, bathroom, all those words, and you find out how many unique, there's only 22 unique words. This neural network gets very, very memory intense when you add more words, because those are basically becoming dummy variables. So that is a big limitation of this, but if you throw memory at it and you throw compute at it, there are examples of this that can learn much bigger vocabularies. The maximum story length is 68. So we're going to essentially create an input that is 68 words by 22 dummy variables. That's the embedding. And another input of the question. So the query or the question, the maximum length that any query was in there is 4 words. So the input to this neural network is going to become the story, which is a maximum of 68 words by dummy variable, by 22 dummies. And the query length is 4 words by 22. So it effectively becomes 72, 68 plus 4 times the 22 dummies is the input. You can see this gets big quickly if you start to add additional words for that. And this is what the vocabulary looks like. Now this neural network will take a while to train. It will take up to, on the faster instance that I'm running this on, it will take about 4 minutes to train. But on slower instances with fewer compute cores, this could take longer. So we want to save the neural network. We also want to save this vocabulary because we need the lookup. This is based on maps, and Python can change the ordering for maps. You're not guaranteed that putting things into the map will always be the same size. So this is the lookup table. This is telling us that 0 is period, 2 is Daniel, and so on and so forth. So when we vectorize these, what it's going to do is it'll change these words into lookups. So Mary is 4. Mary will become a 4. Moved is 15. So that'll become 4, 15, etc., etc. So to build the training set, let me go ahead and execute this part of it. It tells you what the input is going to look like. So you have 10,000 times 68. That's the input vector. 10,000 times 4. And then the answers, which is going to be the vocab size. Let me show you some individual training elements. So this shows you the story. So you'll notice we're always making this be the same length. So the 68, which was the maximum word size of any of the stories. And it's padded to the left. So all zeros at the beginning. And then the actual words that you get here. Now, one important thing to show you, these zeros, the way the padding works, and we have to adjust for this at the end. It's a very important part, and I will show you this at the end. But notice how it says, notice how we have 21 words if you count these two things. If you were paying attention, you probably saw 22 unique words. So the math doesn't quite add up. The additional value that we have is really the empty. So null. 0 is actually null. 0 is the first value in that map, but really the values going in get 1 added to it, so 0 would be 1 and so on. We see that we have to adjust for that at the end. But that is why we have zeros here, so those are actually nulls, and then we get into the actual values of the of the lookup. Same thing here for the question. Now this question was the maximum of 4, so we have no 0 padding. Now we need to compile the neural network. Because Keras does not natively support the end-to-end neural network, there is basically the compute graph has to be created here, at least to some degree. I will show you a little bit of what this looks like. We won't go really through all the details. I would have to take you through the entire paper really to get through that. But we're basically creating 3 encoders, 2 for the sentences, and then 2 for you sort of extract facts out of the sentence, and then you encode those facts with the question to try to build up the answer. So that's why you need 2 encoders for the input, which are there, and then you have another encoder for the question. And the input dimension becomes the vocabulary size, so that it can build out those dummy variables to hold that. The output dimension then becomes essentially the number of values in the next layer. Then we feed these all together, and it eventually all funnels into an LSTM. We're using dropouts, regularization throughout this, and then it finally goes into a softmax on the answer, which is essentially the classification of which of the vocabulary does it feel is the answer to this. And then finally we create the model and train it, and compile it. We don't train it. This part runs pretty quickly. It creates basically the neural network, and the neural network is now built and compiled. This is where we're going to actually train it. We're going to use a batch size of 32 and 120 epochs. Now this is very important. We're going to save the neural network so that since it takes a while to build this, we don't want to just throw it away. So we save the neural network. I added this code from the original example. They did not save the neural network. But we save it to a H5 file, which is a binary file. I also save the vocabulary to a pickle file. Pickle is your standard serialization in Python. And I report on the elapsed time. So I am going to go ahead and run this. And this will take, I'll speed this up, but it'll take, it could take 4 to 8 minutes to actually do this. You see the epoch speeding along here. And it's going through the training set, which is 1,000 elements. So it just continues to go through this. This is not using any sort of early stopping. It is just going to stop at 120. Okay, not too bad. About 4 minutes with this faster AWS instance. This code I'm not going to execute. The neural network was saved. The chatbot was saved to H5 and the vocabulary to a pickle file. If you were running this and you already had the chatbot and the pickle file saved, then you could basically just run this part instead of the training. We're going to evaluate the accuracy. Notice that we do this very similar to the code that we've done before, except look at the input. The input, due to the way that compute graph was structured earlier, the input is actually 2 vectors. It is the inputs and the queries. So the inputs are the stories, Mary went to the hallway, etc. The queries, or the questions, are where is Mary? And we'll run it and we'll print out the predictions. Okay, so this is the typical probability that we've had before. You'll see, now we're not seeing all of the values, but each row is basically showing you the 22 vocab words that you have, is showing you what the probability of each of those words being the answer. Now you can see if you use a decent sized vocabulary where you have maybe 20,000 words, the inputs to this type of network become very, very large. So just like before, we're going to take the argmaxes of these. The argmax now is basically the index of each of these. So that's showing vocabulary word 12 was the expected answer, 9 was the expected answer there, 15, 12, 15. Not all of the words in the vocab list tend to be the answer very often. You can definitely see that certain numbers are chosen more often than others. We can also print out our final accuracy, 95%. That's actually very good. Now I want to show you how to do an ad hoc query. The original example from Keras that I copied these from didn't display the accuracy or show you how to break these vectors apart. So that's all added by this class if you happen to look at the original example that I have a link to just above. They also don't show you how to do an ad hoc query, which I think is probably the coolest part of this. You've trained this great neural network that learns how to read, so you want to try to test it. So I am giving it literally raw text right here. It prints out its vocabulary. It's reminding you, remember, I only know these words. And I tell it, Mary moved to the bathroom, John went to the garden, etc. Where is Mary? And now I run it. Okay, the ad hoc query. This is an area that I added to the program. So you'll see Mary moved to the garden, John went to the garden. That's an easy one. I just kind of made that up and I say, where is Mary? They're both in the garden. So if I run that, it'll say garden. I can change this to Mary went to the bathroom, and it better change its example or its answer there. It's a live demo. Bathroom, good. Mary traveled, and there's several ways you can spell travel depending on the English system. They're using the 2 L's, so I have to use the 2 L's. But it doesn't matter. It still understands that. John went to the garden. There's additional people that you can add into here. I can add Daniel, and we're moving Mary to the hallway, and we can run it. And it's not retraining the neural network. It's using the neural network that has learned to read these type of sentences and answering the questions. I can also change the query and say, where is Daniel? And it adjusts it for that. I'll try, now let me show you a few things that don't work so well. If I say Daniel went to the game, that's outside the vocabulary. It will blow up on that because that's not in the dictionary to look up. So we can't say Daniel went to the game. I have not honestly tried this one, but I'm going to try it here. I'm just curious what it will do. What does it have a concept of time? So if I say Daniel went to the hallway, Mary went to the bathroom, Daniel went to the bedroom. So Daniel has changed his location. He was in the hallway, then he went to the bedroom. What happens if I ask it about that? Okay, it's smart. It figures that out, because if I change this, is Daniel was in the hallway, he went to the bathroom, and then it updates it for the other one. Now, if you think about writing a traditional program to do this, you would be parsing this apart and keeping some sort of state of where everybody is at. The neural network is just figuring out how to do that, and it figures out how to override it with subsequent answers. And I bet there's examples in the training set that teach it that the last answer is correct. You could adjust the training set so that the first answer is correct, sort of like background information, and it would learn that. You could also put the word originally in there and train it for Daniel went to the hallway, Mary went to the bathroom, Daniel went to the bedroom. Where was Daniel originally? And it would very likely learn to know that that was the first location that the given person was in. I'm going to also try something else mean to it. I'm going to ask it, where is Sandra, who does not even appear in this story. So it can't say I don't know. It's saying that she's in the garden. If I had to wager, and let me actually go ahead and print its prediction. So that's the probability. Oh, except I had switched it to argmaxes. So I'm printing out just the probability, its confidence almost. So it is showing that, yeah, it's pretty sure. It's 90% sure. That's the highest probability that I see here, yeah. If I had to venture a guess, it is saying that Sandra is in the garden because in the training set, that's probably where she most commonly was. I don't know. I would have to verify that hypothesis. But this is really a pretty cool technology. This is, you could play with this pretty easily and train it to learn your own types of sentences. You could do things like, where was Daniel originally? Like I had told you there. You just need to generate the appropriate training data for this. And it will literally learn to read those sentences that you have. The more complicated those sentences become, the more difficult, the bigger the neural network needs to be. So the neural network back up here, I didn't really show you a lot of its architecture without having to go into the paper, but you would need to increase that size of 32, and then some of these dense layers here. Right now it's just doing a dense layer on the vocab size, so that's what's fed into the softmax. But you could create some additional dense and regularization layers. In fact, the Keras author is even noting that you would probably need to add those. So this is showing you how you can basically teach the neural network to read completely from scratch. It's limited. It's got a small vocabulary, but for 4 minutes on a 16 gigabyte computer, this is actually pretty good. Thank you for watching the video. In this next module, we're going to look at reinforcement learning. This content changes often, so subscribe to the channel to stay up to date on this course and other topics in artificial intelligence.